Close completely. Yes.
Yeah.
Good evening, sir.
Good evening.
And look, it doesn't matter what level it is. If it's an adiabatic,
Yes. Coding.
Until you start sharing screen.
I'm starting now.
Can start.
The recording now is here. I want you to record in. No, record. This record. Recording now.
It has started recording.
Okay. Record to the cloud. Okay.
Share screen. The PowerPoint slide is it already open?
No, it's not open. It's open. What is? Change it again. Oh, I didn't know. Okay. So, méjì kan.
You can just say
Méjì kan. Open there. Okay. Yeah, good evening. We'll continue our class today. Starting from where we stopped yesterday. I realized that towards the end of the class yesterday, many of you couldn't hear me. But I am sure you heard me up to the time we were about to start with potentiometric titration. potentiometric titration. Potentiometric titration, this makes use of the E cell of the reaction to determine the pH or the equivalent points of such titration. And the normal thing is when you do the normal acid titration, normally you'll be able to see a color change, but in a situation where what you have is very cloudy and you cannot actually say this is when the color is changing. Under that condition, instead of using the normal acid-based titration where you use color change, you use indicator, then you use what we call the potentiometric titration. In this case, the solution of unknown concentration is placed in an anode and is titrated with a strong base. So you have your anode, you have anode in that solution. And then what you now do is you make a plot of the changes you find in the E cell against the volume of the strong base that we are adding. So when you look at that, you make a plot. There's a point where you see there's a sudden change. When you draw lines across the two lines that you have, you see there's a point where there's a sudden change. That point where you have a sudden change is the point we call the equivalent point. I think I should make this bigger. So that is the point which you call the equivalent points. So now, the major difference is that instead of you using the normal color change to monitor what's your end point, in this case, you use when you have the equivalent point to monitor what is your end change. So I say you now use your E cell, either you are measuring E cell against volume or you are measuring pH against volume. So where you have the sudden change is the point where we say you have the equivalent point. So either of these two conditions is necessary for potentiometric titrations. And then the first condition is that the concentration of one of the reactants must change rapidly at equivalent point. That means you have a sudden change and you can see that, okay, this is the point where you have the change. And then the second point is that there must be an electrode whose potential depends on the concentration of the reactant. So there must be an electrode whose potential depends on the concentration of the reaction. So you must have either of these two conditions before you can use potentiometric titration. And a good example that you can use of potentiometric titration is when you are titrating silver with silver ion with iodide ion, and normally you have a precipitate of silver iodide. So normally you won't know when this starts, but you find something cloudy, you won't be too sure. But when you are adding and you are taking pH against volume, you know suddenly, okay, this must be the equivalent point. Then that is what we call potentiometric titration. Now we go to electrolysis. I won't waste so much time on this because I know you are very, very familiar with electrolysis. Just we said earlier that for electrochemical cells, your E0 cell must be positive and that the reactions are spontaneous. But in the case of electrolysis, the one you are very, very familiar with, what happens is that there are chemical changes that are not spontaneous because the redox reaction has a positive free energy. And positive free energy means that the reaction is not spontaneous. And that means the E cells for such is negative. So under such condition, what you do is you have to apply electricity to make sure that there's a driving force, there's movement of electron. And this, when you pass electric current through such chemical reaction, that is what we call electrolysis. So it's like opposite of your electrochemical cell. And under electrolysis, the cell in this electrochemical process, normally they are called electrolytic cells. They are called electrolytic cells. And in most cases, the electrochemical cells we talked about earlier, you have one electrode inside one and inside one container, then you have another electrode inside the other, and then you have the two joined together by a salt bridge. In most cases for electrolytic cells, you have a single electrolyte, and you have two electrolytes inside same component. You have two electrolytes inside same component. So it's the same electrolyte you have for them. But for electrochemical cells, in most cases, you have different electrolytes in the two components. So the condition for electrolytic cells are usually far from the standard condition. You know, when we are talking about electrochemical cells, we are saying standard condition, your temperature, 25 degrees C, your pressure has to be 1 atmosphere. For electrolytic cells, it's just conducted under normal situation because you have to pass electricity through it. So the major differences between galvanic cells, which we also call photic cells, and electrolytic cells are this. The first major difference is that the direction of electron flow is reversed. Is that okay? For electrolytic cell, you have it flowing from the anode going to the cathode. For that of electrolytic cell, it goes the opposite way. Because in one you are generating, in the other you are using electricity in the opposite direction to cause chemical reaction. So the direction of flow is in the opposite cell. And then the anode is the positive electrode in electrolytic cell. Is that okay? The anode is the positive electron in the electrolytic cell. If you look at the galvanic cell we checked earlier, the anode is the negative electrode. So I think you must take note of this. I told you earlier that I'll be telling you some of the differences that you have between them. I'm sure you probably are not familiar with this one before. So just take note of the fact that for electrolytic cells, the directions are different, are opposite, and that anode is positive in electrolytic cell, whereas it is negative in photic cell. And then the third one is that the cathode is negative in electrolytic cell, and whereas it is positive in galvanic cells. So these are the differences that you have between galvanic cells and electrolytic cells. So you have to know this. And remember I told you that time that the common definition of the anode is that anode is where you have anions moving to. Cathode is where you have cations moving to. So that one is a common definition between the two of them. So now, the potential needed for electrolysis. Normally, when you have a photic cell and your E cell, normally for this, which is our popular Daniel cell, is this. This is the inner cell. That's 1.1 fold. You need that to reverse this reaction. You know, before we just turn the reaction and we say this one becomes negative. So to reverse this spontaneous cell to the one that has to be electrolytic. If you look at this now, we have changed what you have on the right hand side to the left hand side, and what you have on the left hand side to the right hand side. So that means you need at least 1.1 volts from external source to push it to the other direction. You know, if the force that is using to go in one direction is 1.1 volt, for you to stop that movement and cause it to go in the opposite direction, you need something that is just a bit smaller than 1.1 volts. I mean, that is a bit bigger than 1.1 volt. So you need a minimum of at least 1.1 volt to make it to flow in the opposite direction. And in practice, to obtain a appreciable product from the electrolytic cell, the potential is often significantly greater than the cell potential. So that means what you actually need will be a bit greater than this for you to be able to have product from your electrolytic cell. So it's like now moving in the opposite direction of what you have normally. And you discover that sometimes when you want to actually do this, the excess force that you have to use over the normal cell potential is what we call overpotential. Now, what you actually need to cause that reaction to go to 1.1 to go the other direction is 1.1 volt. But in reality, when you do that experiment and you want the reaction to go the opposite direction, you discover that you need more than 1.1 volt. So the excess volt that is over 1.1 volt is actually what we call the over potential. I hope you take note of this. That is over potential. And what normally causes that problem is you have some interactions between your electrodes and between your electrodes and your solution and things like that. So those ones will also take something. So that interaction is what we call polarization. So polarization is one of the causes of over potential. And this is very common when the species involved in the electrode reactions are gases. You know, when they are gases, that means the real interactions will not be as much as it ought to be. And normally, you can minimize this when you carefully choose which electrode you are using for one and which electrode you are using for the other. So if you are using inert electrode, that means the interaction between the electrode and the solution may not be so much, and therefore your polarization is reduced and your over potential will be reduced. So for instance, the over potential for the discharge of hydrogen at a mercury electrode is about 1.5 volt. That is, you need extra 1.5 volts. Whereas if you use, instead of using mercury electrode and use platinum electrode, that is for cathode this time around, then it is 0. So you can see the difference. So actually when you are doing electrolysis, if you are a chemist and you know what is the right electrode to choose, then you'll be saving a lot of money by not using a long electrode. Because in this case, it is 0. If you decide to use a mercury electrode, you have to be supplying 1.5 volts extra. So, and the over potential for production of hydrogen and oxygen, if you use platinum electrodes, it's about 0.6 volts. And if you therefore insist on applying 1.23, which normally is the cell potential, then that means you have about 1.6 that you actually have to apply. But normally the component of what you have, the evolution of this causes about 0.5 and 0.1 respectively. That is what makes up to your 0.6 volt that you have there as over potential. Another important factor that actually determines the potential you need for electrolysis is the presence of more than one species at the electrode. You know, when you have more than one species at the electrode, you have to determine which compound is going to be discharged and which one is not going to be discharged. And that means you have competing reactions. So you have to decide which one you will actually have and which one you are not going to have. These are some of the things you have done normally at your school site, and that shouldn't be a big problem for you. So if you are using electrolysis of sodium chloride for a sample, if it's in molten form, you only have only one oxidation and only one reduction because there's no solution there, there's no water. That is when you have it in molten form. And your reaction is just simply going to be this. And the things you have to discharge will just be chloride going to chlorine, and then you have your sodium going to sodium liquid. And with that, you don't have any problem. So you have your oxidation and your reduction. There's no water, and therefore you know what and what you are doing. But when you have water, now instead of having only chlorine, you only have water now also going to water. Are we going to oxygen plus 4 hydrogen plus 4 electrons? And then for your reduction, you also have sodium, which you have here. And in addition to that, you also have your hydrogen. So you also have your water, in this case, going to hydrogen plus 2O minus. So now, you have competing reactions at the oxidation level, and then you have competing reactions at the reduction level. So if you look at this is minus 1.36, this is minus 1.26. Now, when you have these two competitions, the question is, which one will you prefer? Minus 1.36 or minus 1.26 and 1.23. So it's like you are in debt and you are asking which debt will you be willing to settle. You know, normally you go for the depth that is easier to settle. So ideally, somebody wants to go for the oxygen production here instead of chlorine. And in this case, you see you have sodium is minus 2.71 and your hydrogen is minus 0.83. So now the choices you have to make, that means the one that will be discharged for each of the half reactions will be, the constraining factor will be what amount do you need to discharge each of them. And of course, you go for the lower one, just like I said earlier. So in the case of oxidation, I've told you you prefer the 1.23 because it's smaller than the other one. And in the case of the reduction, you prefer that of hydrogen because it's actually smaller than the other one. The other one is minus 2 point something. So, and this is just minus 0.83. So that means this will be preferred here, this will be preferred here. Now you have something completely different from where you have it in molten form. So you can just see the kind of difference you have when you suddenly change the composition of your electrolyte. So in reality, chlorine is discharged at the anode. And now the question you ask is why is chlorine discharged at the anode? The chlorine is discharged because your oxygen has overpotential. Remember, we just talked about overpotential of oxygen now because it's a gas, and the interaction of that with the anode is going to cause an overpotential. And this will normally increase the charge that you need to discharge oxygen to 1.73, which is greater than what you have before. So you can see now the reason why you are not having this and you are having chlorine. That is because of overpotential created by hydrogen, created by oxygen in this case. So now an exception can also occur at the cathode if you use mercury electrode. If you use mercury electrode, then hydrogen is also going to have a high overpotential, and in that case 1.5, that means it will make sodium will be discharged if you use mercury. But if you don't use mercury, then you don't have that problem. So the choice of what is discharged and what is not discharged, I've told you now, depends on the electrode potential, and it also depends on the type of electrode you have used, because that may create some overpotential caused by the fact that there is polarization. So we go to laws of electrolysis. I'm sure you are familiar with this. Faraday's laws of electrolysis, often we don't. So the first one says that the mass of an element produced at the electrode is proportional to the quantity of electricity passing through the electrolytic cell. So simply, this is just the formula you have. Mass proportional to Q. That is quantity of electricity. And normally, Q is expressed in coulomb. And the quantity of electricity normally is defined in terms of the current multiplied by T. So if you have current multiplied by T, that means your Q is equals to IT. And that means you can now go ahead and where the standard unit of I is ampere and that of time is second. So even when you have your time in hours or days, you have to convert to seconds. So going on with that same first law, right? This second law, the second law simply says that the mass of an element liberated at an electrode will be proportional to the equivalent weight of the element. Proportional to the equivalent weight of the element. What equivalent weight simply means is the amount that you discharge, that will be discharged by 1 Faraday. And that means you are discharging 1 mole of electron. 1 mole of electron will normally discharge 1 Faraday. So what this one is saying is that M is proportional to equivalent mass. Now, equivalent mass, for instance, if you have sodium, sodium is Na plus. Sodium is Na plus. It has just plus, so 1 Faraday will discharge 1 mole of sodium. And therefore, equivalent mass of sodium will be 23. Now, if you have calcium, for instance, calcium is 2+. Now, to discharge 1 mole of calcium, you need 2 moles of electron, 2 Faradays. What 1 Faraday is going to discharge will be 20 gram. So that means the equivalent mass of calcium is going to be 20. I hope you've gotten it. So it's like discharge, you divide by the number of charges you have on that element, on that, the element. So that means equivalent mass is equal to the relative molecular mass or the atomic mass divided by the number of moles of electron that you need to discharge it. That's what I've just explained. So for instance, for copper now, your copper is 63.5. That means the equivalent mass of copper is 31.75 because that is copper 2. So you divide by 2. And whereas for silver is 108, equivalent mass is also 108. So the equivalent mass of an element is normally defined as the mass of the substance that is discharged by 1 Faraday. I think I mentioned this earlier. And so we go on, and you know that 1 Faraday will discharge 1 mole of electron. 1 Faraday will discharge 1 mole of electron. And your 1 electron has a charge of 1.602 times 10 raised to power minus 19 coulomb. And you know, in 1 mole, you actually have how many electrons you have in 1 mole. So you know that is 1 mole will be 6.022 times 10 raised to power 23. So if you want to know what you actually have, your Faraday, 1 Faraday of electricity will actually be what you call a product of this charge per electron and this electron per mole. And that is how we have gotten Faraday constant. I know you know Faraday constant all along, but I'm not sure if you know how it was derived. This is the way it has been derived. So when you look at this, this is now coulomb per mole. So you have examples here. What mass of metal will be discharged at the cathode when a current of 10 ampere is passed through a molten silver and sodium chloride for a period of 4 hours. So all you simply need to do is just go on with the calculation. You calculate the quantity. You have 10 ampere, that is your I. Your T now will be 4 hours. 4 times 60 times 60 will give you this. And therefore, your Q will be equal to 10 times this value, and you have that value. So the balance equation at the cathode normally will be, you have sodium plus 1 electron to give you this. And 1 Faraday will deposit 1 mole of sodium, that is 23 grams. Then the question is, what will this amount will deposit? So that this will now deposit, you can now calculate what this will deposit. So one coulomb will discharge 23 over this, and then 144,000 will therefore deposit 23 over 96485 times this, and that means you have 34.3 grams. So that is how to do that. I'm sure you are familiar with that. And I have another question here. Calculate the oxidation number of chromium in an unknown salt. If the electrolysis of the salt yields 9.71 gram of chromium at the cathode after 10 ampere of current is passed through the cell for 1.5 hours, the relative atomic mass of chromium is this. So if you are to calculate the oxidation number of chromium, that means you are asking how many Faraday will actually discharge it. So the way to go about it is first calculate the Q. Q is I times C. Q is I times C. So your I is 10, your T is 1.5 hours. That is 1.5 times 60 times 60, and that is 540. So when you multiply that, that is 5,400, and then your Q now will be 54,000. So now you have determined your Q, and you know 1 Faraday is going to liberate 1 electron, and therefore how many electrons will this liberate? That will be 54,000 over 96,485 moles of electrons. So now you discover that this is going to liberate 0.56 moles of electron. Now, if you go on with this, the number of moles of chromium deposited is you have 9.71. So you divide it by 52, and that is 0.187. So 0.187 was deposited, mole of chromium. And you already determined earlier the amount of this thing that you have there, the number of moles that you have there. So what you now do is you compare this ratio to this ratio. So you have this amount discharged, and you have this that has discharged it. So that means to every one of this, there must be 3 of this. So it's ratio 1 to 3. So that shows that for every mole of chromium, you have 3 charges. And that means that your chromium is actually chromium 3+. So that is the way to look at this. There's this other example that if you have an electrolytic cell, and they calculate the mass of aluminum that can be produced by electrolysis of aluminum oxide dissolved in a molten cryolite Na3AlF6 in 1 day if the electrolytic cell operated constantly at this ampere. And you see the time you want 1 day. 1 day is 24 hours. So you can go ahead and calculate. So this aluminum, normally you need 3 moles. So that means for 27 grams, you need 3 Faradays. So you go ahead and now calculate. 3 Faradays is actually 3 times this. That's the amount you need. You calculate your Q now. Your Q will be this number of amperes you have been given, then multiply by 24 hours times 60 times 60. So you have your time there, and your Q is actually 8.64 times 10 raised to power 9. So that is the quantity of electricity that is produced. And then for 1 mole, you need this. So the next thing you now just go ahead and consider is, if you need this one for 1 mole, how many will this one discharge? So that will be this quantity divided by this quantity multiplied by 27. And that gives you your answer. So we go to another step, that is electrorefining. Electrorefining, electrosynthesis, and electroplating. I know you are very familiar with electroplating, so I will just try and define these things so that we move on. So electrorefining is a situation where you have electrorefining of metal involves the position of pure metal at the cathode from a solution containing the metal ion. What the advantage of this is, if you want to produce metals that are very, very, very pure, then you have to use the electrorefining method. You spend a lot of money, but normally they are very good conductor. For instance, if you want to produce copper that is for electric conductivity, then you have to use that. So you produce high grade purity of conductor that can be used to conduct electricity. Not the type that you use for metallurgy. You know, if you just take raw copper, you melt it, you have good copper, but it's not going to be as pure as the one you can use to conduct electricity. So normally when you have raw copper and you do this kind of thing, what you normally have at the end is that you have some impurities there that are like silver and gold. So people still go ahead and do it because these are what we actually call the anode mud. So when you spend a lot of money doing the electro refining, you come up with this, and of course the money you make from the silver and gold you sell will be enough to cover up for the money you have spent for electro refining. So I think that's what this is just saying. Now, electrosynthesis. Electrosynthesis is also similar to electro refining, but of course, electro refining, you are not changing chemical composition. Electrosynthesis, you are producing a new thing, and you are using electrolysis to produce this. And a common example that you will do is manganese 4 oxide, which is used in many alkaline batteries. So electrosynthesis of MnO2 is carried out in the solution of MnSO4. So normally you have MnO2 is produced at the inert electrode by the oxidation of your manganese 2+, and this is the equation for that. And so this is the equation for the electrosynthesis of MnO2. So know the difference between electro refining and electrosynthesis. So I won't waste time on electroplating. I'm sure you are familiar with that. You electroplate wristwatches, gold, neck chain, and quite a number of other things. So I won't waste more time on that. So I go to batteries. I'm sure you're also familiar with batteries. But what happened is that definitely a definite definition of battery is that it's a device that stores chemical energy, which is later released as electricity. That means they are spontaneous. They are released as electricity. You have chemical components, then later they are released as electricity. So some batteries have just a single photovoltaic cells, while some have a number of photovoltaic cells that normally are connected in series. And there are 3 major types of batteries. 3 major types of batteries. The first ones are primary batteries. They are sometimes also called primary cells. Is that okay? So when you have primary batteries, primary cells, we are referring to the same thing. Just like I said earlier, they are galvanic cells. They produce electricity from chemical reactions. And the primary ones, the major characteristics here is that they are not reversible. Once their reactants are converted, the supply of electricity stops and the battery is dead. Your elephant battery, I'm not sure how many of you knows what elephant battery is. Or tiger battery, I'm sure probably you may know tiger because that one still exists now. This tiger battery that is bigger than the alkaline batteries. So that's an example of a primary cell. Then the secondary cells, they are also galvanic cells. But in this case, the reactions that they use to produce electricity can be reversed. That means you can apply electricity and reverse that reaction. And that process is what we call charging. And that recharging can be done several times before the battery will be weakened up and then you discard it. And a common example is the type of batteries you have in cars. This lead acid battery is a common example of secondary batteries. And the third type, which is not a very common one, is the flow battery. Flow batteries, we call them again fuel cells. They are electrochemical cells in which you have combustion reactions and you generate electrical energy. But the thing is that it is continuous. It's only when you supply combustible materials, hydrogen and oxygen, that you have electricity produced, or you supply methane or whatsoever. That's when you have electricity produced. So in the absence of that, there's no electricity. So the flow batteries means you are supplying energy and the energy is being converted to electricity. So you have, we'll quickly go through examples of primary cells. The Electro dry cell is a common example, and that was first came up in 1860 by the French engineer Electro, and the cell produces about 1.5 volts initially. So normally when you use it over a period of time, The moment the voltage drops to about 0.8, then you don't have electricity produced again. So that means once your voltage drops below that, your battery is already dead. And and this is because the products are accumulated. When you have reactions that are taking place there, the products inside are accumulated. Then after, if they are accumulated, the potential drops. But if you leave it after some time, you still go back to that same battery. The product that has accumulated on it, you probably have dispersed a bit. Then you discover that your voltage climbs up to around 1.3 volt, and then you still discover that you can use your primary battery. For instance, I remember when we were young, when you use battery and it's no longer blinking, it's no longer shining, what you do is you go and put it in the sun, and that will hasten the product to disperse. The moment that is dispersed, you go back and use your battery, you discover that it still works. So it's because it dispersed the products that actually accumulated on it. So these cells are called dry cells because there are no liquid in them. Though normally when it starts getting bad, you see some water coming out of it, but at that level, it's really not a battery. So the container of the cell normally acts as the anode, and often it's a zinc metal. When you peel the paper, you see one zinc that is like a wrapper for it. That is the anode, and it's a zinc metal. And the reaction there is this. You have zinc going to zinc 2 plus 3 electrons. And the cathode is the carbon rod. When you look at it, the carbon rod inside, the one that produced outside. So that is the cathode. And the reaction is a complicated reduction of manganese 4 oxide to manganese 3. An example is this. So you either have it this way or you have it this way. So that is the type of reaction you have there. And the electrolytes normally is a moist paste of ammonium chloride, zinc chloride, and manganese 4 oxide. You can see these 3 compounds together forms the electrolyte in this case. We said a moist paste of such. The OH ion from the cathode that you have from the cathode reaction here will normally migrate towards the anode, and that will react with your silver, your ammonium here, and then ammonium from your this, and then begin to form ammonia gas. Is that ammonia gas that actually causes the problem? No, the moment you have that built up, then your battery will show that, yes, it is already getting used up. And that's the equation for the reaction. And that is when you say, okay, the product built up, and then the battery is no longer functioning. So the build-up normally disrupts your zinc, and then you have this complex form, and then it becomes a problem because you have a chloride of this, and then your battery stops working. And since it's not a reaction that can be reversed, except if, like I said earlier, some help you to disperse some of it, or after you leave for some time, it disperses, you have some, but you cannot reverse that reaction. So when current is drawn rapidly from it, then you have ammonia produced, and that also builds up, and the voltage drops. So these are the problems with this. And remember that this electrolyte is slightly acidic, and that is part of the problem. The electrolyte is slightly acidic, and that is part of the problem. So what is sometimes done is to use an alkaline battery, and you discover that with your alkaline battery, they are smaller and they don't produce water when they are bad, like the electrolytic dry cell will do. If you look at this diagram, this is a typical diagram of your primary cell. So you can see it, this carbon rod here, that's the graphite, that's the cathode, and then the container here, which is the wrapper here, is the anode, and you have the reaction. So for alkaline cells, instead of using NH4Cl, what you do is to use potassium hydroxide, or you use sodium hydroxide. And in that case, the formation you have is going to be zinc hydroxide solid instead of what you had before. And it has the following advantages. You know, it can be used over a wide range of temperatures because the electrolyte is more stable. Is that okay? You can use it at lower temperature and you can use it at high temperature. You know, in this place, we often have high temperature, 25 and above, so we don't have problems of temperature. But alkaline cells has that advantage. Alkaline cell has that advantage over the normal cell. And then it requires just little electrolytes. Hence, the sizes are normally small. That's why they are smaller than the other one to produce electricity. So these are the advantages. Then, because ions move through the electrolyte, it produces more. So it produces more power and a steadier current. You know, they don't get used up readily like the other one. The major disadvantage of this battery is that it is more expensive. And of course, the packing, you see, the sealing is much better because they want to prevent leakage of hydroxides. So this is your common lead acid storage battery, which is what we use in cars. And I'm sure you must have done this at secondary school. So the area of it is, the larger the area, the more electricity is given out. So this one normally it can be reversed. The reaction can be reversed. That's the major difference between the secondary batteries and the primary batteries. And remember, lead acid battery is also called the storage batteries. So electrodes are normally initially in the plate of lead antimony, and all will be covered by lead sulfate. And your electrolyte in this case is sulfuric acid. So you check most of your batteries, what you have there will just be dilute sulfuric acid. So during the first charging, what you have is that your lead sulfate on one of the electrodes will be reduced to lead, and that is at the anode, while the other one at the cathode is oxidized to lead 4 oxide. So your PbSO4 is reduced to lead, and your PbSO4 is also oxidized to PbO2. That tells you what type of reaction: proportionation or disproportionation reaction. So I'm sure you should be able to answer that when you have it. So this is a typical secondary cell, a typical lead acid storage battery cell. You can see the plates that are inside it and the way they are connected together. So the more surface area you have, the more current you produce. And the reactions are just this. For the discharging, you have this for the discharging. For the charging, you have the opposite reaction. So when it's discharging, you have PbSO4 2 minus going to PbSO4 plus 2 minus. When you are charging it, you are changing it from PbSO4 to Pb plus SO4 2 minus. So its discharge standard is 0.386 volts. And the reaction at the cathode, I told you that one you are producing Pb, the reaction at the cathode. So you have the forward reaction is for discharging and the backward reaction is for the charging. So normally this one, the potential is 1.682 volts. So you can see it's a bit greater than what you have for the other one. So when you have a combination of the two, then you have this equation, and your overall, because you have added the two together, your overall discharge voltage is going to be 2.068 volts. So that is your lead acid storage battery. And this is when your concentration, this concentration of electrolyte, once it's decreasing, you discover that you are not going to have enough electricity from it again. And that's why they sometimes use hydrometer to check the density of the sulfuric acid. So you can always check the density of sulfuric acid to see whether it's fully charged or not. Otherwise, you may need something from outside to charge it. So I'll just keep over this. And of course, normally when you are charging, you have to leave open. I think that is important. You have to leave it open, because if you don't leave it open, the gases that are being produced, you may have explosion. So when you are charging batteries, normally you leave the cells open. And so the major disadvantage of this, which is very, very important, is that they are heavy. Is that okay? That's the major disadvantage. They are heavy. The second disadvantage is the fact that they are corrosive. Is that okay? They are corrosive, and that's a big problem. So you have various types of other batteries, secondary batteries, which you can see in your notes, and these are examples. So I will you have the other examples. This is zinc battery. This is the type you have in your wristwatches. You have the advantage of that is the mercury that you have there. The silver zinc is actually the type you have in your wristwatches, the type you have in your calculator. That is the silver zinc battery. And this is the anode equation, the cathode equation, the net equation, and of course, this is very, very good. If you have them of the same size with the lead acid storage battery, then they are going to be much, much powerful, at least 6 times powerful than the lead acid storage battery. Now, the last one is the flow battery. That is what we call fuel cells. So I've told you, for fuel cells, they convert chemical energy to electrical energy, and it's only when you bring fuel that you have electricity. And in most cases, you have hydrogen gas and oxygen gases. So the fuel here is hydrogen, and it's passed over electrode, while oxygen is passed over the other. And then the electrolyte normally in fuel cells is 25% potassium hydroxide. An example where the oxidation reaction is this, the oxidation reaction is that, the cathode reaction is that, and this is so this is what you actually have as the net reaction. You see, this is the simplest form that you have. You can also have it in forms of methane, not just hydrogen. This is the simplest and the most common one. And already now you have in the US cars that are running on fuel batteries. And then fuel batteries are, well, this is an example. This is a typical diagram of fuel battery. There's another example I think I need to show you. Sorry, I'm trying to get my... Okay. Okay. So now, you see, in this case, the reaction is in acidic medium. And normally, because you supply, then you get, you don't measure this one in terms of potential. You measure this one in terms of efficiency. And the efficiency normally has to deal with the delta G of the reaction vis-a-vis over delta H of the reaction. So when you are dealing with fuel cells, you are talking in terms of delta G over Hello? Are you hearing me? Hello?
That's it. Okay, it's on.
Hello? Are you hearing me?
Okay, they're responding, yes.
Okay. So actually this is the last slide, and what I wanted to say before the laptop went off was the fact that you have this type of fuel source in electric eels. Electric eels is a type of fish, and you also have it in catfish. And what normally happens is that the food they eat actually act as the fuel for them, and you discover that each cell they have produces about 1.5 volts. So when you have an electric eel that's about 1 meter, that means that will be generating about 350 volts. And that tells you that's a lot of current. And that's why divers sometimes have to be extremely careful to make sure they don't come in contact with this. So normally the head of the electric eels act as their cathode, while the tail act as the anode. And electric eel, normally you see in most cases is blind, because the electricity it generates also kills itself, because the moment anything comes close to it, the way it sucks that actually it affects it again. So this is a natural example of fuel cell. So I'll be ending my class here. So when we have the opportunity, we'll be able to interact more, and I'll advise you go and solve all the questions behind the book. I've given you some before, so you have to go and solve all the other ones. So with this, I want to say bye-bye. I hand you over to the next lecturer, Dr. Latunde, who will be taking you as from Monday. Thank you and God bless. So, is which book is the book I introduced to you in the beginning? That is the physical chemistry textbook. You can get it in the bookshop, the university bookshop. I told you that's where all the questions I gave you earlier, they are there. So go and solve all the other problems that are there. And if I have time, really, I can actually leave some exercises for you on the LMS. So it's done.
Yes,
So let me stop recording. Then so okay, stop the slides.
take cloud recording also for the classes. And yeah, need to you can always access.
Leave meeting. Mo fẹ́ end the class. Leave.
Okay.